AB 3D MOT, a baseline for 3D multi-object tracking, and new evaluation matrix. Our work contributes a strong and simple 3D MOT system and a standard 3D MOT evaluation tool. Although there are different categories of 3D MOT methods, recent work tends to focus on this standard tracking by detection pipeline to approach 3D multi-object tracking. First, the tracking by detection pipeline takes sensor data as inputs, where the sensor data is often LiDAR point clouds or RGB frames, or the combination of them. Second, we feed the sensor data into a 3D object detection module to output detection results, often represented by 3D bounding boxes. Then, a data association module takes the bounding box results from the detection module as inputs to output final object trajectories in the 3D space. Finally, the evaluation module measures the performance of output trajectories via a bunch of metrics such as multi-object tracking accuracy and multi-object tracking precision. The evaluation module is also very important as it might drive the direction of future 3D MOT methods. Okay, we have talked about the standard pipeline. What are the limitations of prior work? In this work, we address two limitations. First, prior 3D MOT method tends to focus too much on the novelty and accuracy, while ignoring practical factors such as runtime speed and system complexity. Second, an appropriate 3D MOT evaluation tool is not available, and prior 3D MOT methods cannot be fairly compared. To deal with the limitations, we propose two contributions. First, we provide an appropriate 3D evaluation tool to standardize future 3D MOT evaluation. Second, we introduce a strong yet simple 3D MOT system with the fastest speed. Before diving into our 3D MOT system, let's first talk about the evaluation. So, what are the issues for current 3D MOT evaluation? Let's first look at the common matching criteria, intersection of union, which many of you are familiar with. The intersection of union is used to measure the accuracy of the predicted box with respect to its ground truth. It can be measured in 2D by computing the area on the image plane, or it can be measured in 3D space by computing volume. Both 2D and 3D IOU are useful, but should be used in different cases. Although 3D MOT system can obtain 3D bounding box trajectories, the pioneering 3D MOT dataset, KT, only supports evaluation in the 2D space. As a result, the common practice for 3D MOT evaluation in the KT datasets are the following two steps. First, project the 3D MOT result onto the image plane. Second, run the 2D MOT evaluation code provided by KT, which of course will give you 2D MOT results, not 3D. To deal with this issue, our solution is to simply upgrade the matching criteria to the 3D space. For the KT datasets, this means that we replace the matching criteria of 2D IOU with 3D IOU. Our 3D MOT evaluation code has been released and reached more than 800 stars on GitHub. Please check out if you are interested. In the meantime, we work with Nutanix collaborators to extend our 3D MOT evaluation to the modern USINS datasets. We hope that our new evaluation can help standardize future 3D MOT evaluation. Okay, we have upgraded the matching criteria to the 3D space. That is good. Are we done with the evaluation? Is there anything we can improve further? Well, let's first review the primary metric used for ranking MOT methods, the multi-object tracking accuracy metric, abbreviated as MOT. MOT is a single scanner computed by summarizing a few important metrics, such as false positives, false negatives, and identity switch. We can see in the figure here that MOT performance is changing at different recall points, while being the highest if we choose the recall point at about 0.9 for this method. So we can tell that the MOT performance is measured at a single recall point, and it does not represent all other points on the curve. Therefore, the MOTE matrix cannot help us understand the full spectrum of accuracy of a MOT system. Okay, now we know that MOTE measured at a single recall point is not ideal, so what can we do to improve it? Our solution is to compute the integral matrix by measuring the area under the curve, as shown in the shadow of the figure. We call this new integral matrix as average MOTE or A-MOTE. A-MOTE is analogous to the average precision matrix widely used in optic detection. Also, A-MOTE can account for all the points on the curve. In other words, it can reflect the full spectrum of the MOT accuracy. Okay, so far we have an improved evaluation tool for 3D multi-object tracking. Let's now talk about our proposed 3D MOT system. To deal with the limitation, we proposed a baseline system for 3D MOT. Our motivation is to reduce the system complexity and increase the runtime speed. This leads to the simple design of our system, which is a combination of the 3D comma filter and Hungarian algorithm. Our 3D comma filter is a simple extension to the standard 2D comma filter widely used in 2D MOT. Specifically, we add objects 3D properties into the state space, such as 3D object location, speed, heading orientation, and size of the objects. Due to the simple design, our system can run at a very high speed, about 200 fps for cars and about 470 fps for pedestrians, and about 1200 fps for cyclists. In the meantime, a strong performance can also be achieved, which is competitive to other more complicated systems. Now, let's take a look at our system pipeline, which includes 5 modules: 3D object detection, state prediction in the comma filter, and Hungarian algorithm for data association, state update to obtain the trajectories, and finally the birth and death memory module for tracking management. Now, let's talk about the result of our 3D MOT system. First, we evaluate our 3D MOT system on the KD datasets for the car category and compare with 2 learning-based baselines that have higher system complexity than our system. As the matching criteria of 3D LU equals to 0.25, we can say that our system outperforms 2 baselines in most of the matrix. It's worth noting that our system is the fastest, which runs at about 200 FPS with CPUs, while the baseline requires GPUs and ran at a much lower FPS. Moreover, we evaluate all systems with stricter matching criteria, such as 3D LU equals 0.5 or 0.7. Although the performance goes down for all methods, our system still outperforms the baseline. This shows that the strong performance of our system is robust to different matching criteria. Okay, qualitative results. We visualize the 3D trajectory outputs as colored 3D bounding boxes. Each colored box represents a single object tracked by our system. We show that our system can produce stable 3D trajectories over time across different sequences. Also, we show our results for pedestrians and cyclists. Thank you for watching.